I got this puzzle game as a Kris Kringle gift last year. It's called Color Cube Sudoku and it's produced by ThinkFun. The goal is to arrange these colored blocks so that each color appears exactly once in each row and column. The packaging says that there are 500,000 solutions, and today we are going to test that claim by completely enumerating all of the solutions. We're also going to run into some nice group theory trivia along the way. If you have this game, this video will be a massive spoiler, obviously. The first question to answer is, what can we do with a single cube? Each cube has 4 colors, and by rotating the cube, we can rearrange those 4 colors. How many of those arrangements can we reach? Well, if we could choose how to order these colors arbitrarily, then the total number of arrangements, called permutations, would be 4 factorial. That's because there's 4 options for what color goes in the top left corner, and then once we've decided on that, there's 3 options for what color goes in the top right corner, and then once we've decided on that, there's only 2 ways to arrange the 2 remaining colors. And 4 times 3 times 2 is 24. On the other hand, this cube has 6 faces, one of which we can choose to be on top, and then that top face can be rotated 4 different ways, and 4 times 6 is also 24. Now, this doesn't guarantee that we can reach every arrangement of colors. It's possible that 2 orientations give the same arrangement of colors. But, as it turns out, this doesn't happen. Amazingly, the cubes are colored in such a way that we get every single one of these 24 arrangements. This relates to a fun bit of trivia about group theory. A group is a set of things with an operation satisfying certain axioms, and typical examples of groups are sets of transformations, things like rotations and permutations. It turns out that the group of rotations of the cube is isomorphic to the 4th symmetric group S4, the set of permutations of 4 things. By isomorphic, I mean that there is a map between these groups which respects their operations. This map takes a rotation and looks at how it exchanges the 4 diagonals of the cube. It's a nice exercise to check that this map is in fact bijective. Now, if we take a look at one of the cubes in Color Cube Sudoku, you can see that opposite corners have the same color, as though we are coloring the 4 diagonals. So each rotation corresponds to a permutation of the diagonals, which in turn means a permutation of the colors. Neat! It's not hard to figure out which rotations will swap 2 colors or reflect the colors vertically or horizontally. So now we don't have to worry about the cubes, and we can instead think of them as just a set of 4 colors that we can arrange however we want. This means that cubes are actually kind of irrelevant to the puzzle of Color Cube Sudoku. And the colors are also kind of irrelevant. You could replace all the colors with numbers or arbitrary symbols, and the whole concept would still work. To be honest, I prefer symbols to colors, not because I'm a mathematician, but because I am slightly colorblind. My eyes are really struggling with these specific shades of red and green. Accessibility is important, ThinkFun. Also, can we really call this game Sudoku? The whole point of Sudoku is that you're given a number of starting clues in such a way that you are forced towards a unique solution. But with this game, the goal is just to find any solution. The manual does have a couple of bonus challenges with additional constraints, but each of these has multiple ways of solving it as well. So this game isn't about colors, or cubes, or Sudoku, despite the title. Anyway, now that we know how an individual cube functions, the next question is, what combinations of colors appear on the cubes? There are 6 colors, and the number of ways of choosing 4 things from a collection of 6 is 6 choose 4, which is equal to 15. But we don't have 15 cubes, we only have 9 cubes, so we're missing a couple of combinations. It turns out that we can group the 6 colors into 2 families of 3. One family is red, yellow, and blue, and the other is green, orange, and white. And each cube uses exactly 2 colors from each family. That gives 3 options for each family, and 3 times 3 is 9. You could figure this out yourself by examination, or you could just look at the manual which spells this out explicitly. These 2 families of 3 are going to be very important for solving the puzzle. So when I was first attempting this puzzle, I decided the best thing to do was to just try putting in cubes at random and see what happens. Filling the top 3 spaces without having 2 colors in the same row is pretty easy, and then the next 3 spaces are not particularly challenging either. But then at the 3rd row I ran into problems. The first column is currently missing the colors blue and green, while the second column is missing the colors blue and white. But that means I need a cube with 2 copies of the color blue, which we don't have. This reveals an extremely important fact, which is going to completely determine how we position the cubes. If 2 cubes are in the same row or column, then they must have all 6 colors between them. If there is a color that they do not have, then the 3rd cube in that row or column must have that color twice, which is not possible. Because of the way the cubes are chosen, we know that there are 3 cubes missing the color red, and these cubes cannot be in the same row or column as each other. Similarly, there are 3 cubes missing the color blue, and 3 cubes missing the color yellow, and we can do the same with green, orange, and white. So for now, let's ignore the problem of how each cube should be rotated, and let's just focus on the question of how to position the cubes in the grid. We'll start with the 3 cubes that are missing the color red. These have to go in different rows and columns, and an easy way to do this is to place them along the diagonal like this. But I could also take 2 of these cubes and swap their rows or columns, and that will give me another starting position. In total, there are 6 possible shapes in which I could position these cubes, and for each of these 6 shapes, there are 6 ways of ordering the 3 cubes within that shape. So that makes 36 total starting positions. Now, at this point, we have to ask, does it matter which starting position I use? Is it possible that some of these positions lock me out of a solution? The answer is no, it doesn't matter, and here's why. Let's suppose that for one of these positions, I am able to find a solution. Hold on, let me just casually solve the puzzle to get an example. There we are, and just for clarity, let me label the 3 cubes that we started with. Using this solution, I can easily generate more solutions by permuting the rows and columns. For instance, I could swap the first 2 rows of cubes, and I will get another valid solution. We still have all 6 colors in each row and column. Hopefully it's not too hard to see that by permuting the rows and columns, I can get these 3 starting cubes into any positions that I like. So if one starting position has a solution, I can convert that into a solution for every other starting position. This means that it does not matter which starting position I use. There's a way to describe this in the language of group theory. Let's call the set of all solutions X. There is a group whose elements are transformations of this grid, given by permutations of the rows and columns of cubes. I'll call this group G, and it has 36 elements. G has an action on X given by applying a transformation to a solution. This splits X into subsets called orbits. An orbit is obtained by taking some element of X and applying every single element of G to it. 2 elements are in the same orbit if and only if you can get from one to the other via the group action. My claim is that every orbit has exactly 36 elements, so to get the number of elements of X, we just need to find the number of orbits and multiply it by 36. The only way that this claim could be false is if there is some solution x and a non-identity transformation g, such that G applied to X is equal to X. But each element of G gives a different rearrangement of these 3 starting cubes, so this is not possible. This is a special case of a more general fact called the orbit stabilizer theorem. For a group G acting on a set X, the stabilizer of an element x is the subgroup of G consisting of elements whose actions send X to itself. The orbit stabilizer theorem is the fact that G1 applied to X equals G2 applied to X if and only if G1 and G2 are in the same coset of the stabilizer of X. In our case, where G is the group of permutations of rows of cubes and columns of cubes, and X is the set of solutions to Color Cube Sudoku, every single stabilizer subgroup is the trivial group, consisting of just the identity transformation. Thus, distinct elements of G send X to distinct solutions, so every orbit has exactly 36 elements. Okay, so now that we know that it doesn't matter where we place these 3 starting cubes, I'm just going to choose the simplest arrangement, which is to place them along the diagonal in some chosen order, which I will take to be missing green, missing orange, and missing white. Next, let's take a look at the 3 cubes that are missing the color blue. The first of these is red, yellow, orange, and white. This is missing the color green, which means it cannot go in the same row or column as this top left cube. That means we only have 2 possible places we can put this cube. It's not hard to check that once we've chosen one of these 2 places, the locations of the remaining cubes are completely determined. For instance, this cube is missing both blue and orange, so it cannot be in the same row or column as either of these cubes, which means it must go here. This cube is missing blue, so it cannot be in the same row or column as these cubes, and so on and so forth. Now, once again, we have to ask the question, does it matter which of these 2 positions I choose? And once again, the answer is no, it does not matter, and here's why. Let's suppose that I am able to find a solution after placing this 4th cube in the center right space. Hold on, let's get an actual example again. Using this solution, I can produce a new solution by taking the transpose of the entire grid. This means flipping all of the colors along the top left to bottom right diagonal through a combination of swaps and rotations. If we do this, we've found a new solution in which this red, yellow, orange, white cube is in the bottom middle space. And this also works in the other direction. If we have a solution for this configuration, then we can take the transpose operation again to move this cube back. This means that it doesn't matter which of these two positions we choose, because a solution for one guarantees a solution for the other. So from now on, I'm just going to assume that we're starting in this position, with the red, yellow, orange, white cube in the middle right space. We've now solved the problem of positioning the cubes, and now we just have to rotate them. At this point, it's not too difficult to find a solution by trial and error. You've already seen me do it multiple times. But if we want to find all the solutions, there is still a bit more we can do before we resort to brute force. If we add this transpose operation to our group G, we get a new group with 72 elements, because 36 times 2 is 72. And everything we said before about orbits and stabilizers still applies. But we could go further. If we can expand this group action as much as possible, that will make it as easy as possible to count solutions. Here's another symmetry that we can use. Given a particular solution, I can swap the first two columns of colors by flipping each of these three cubes horizontally. I can do the same with the middle two columns and right two columns, as well as these three pairs of rows. Let's redefine G to include these transformations. This is not exactly a direct product of groups. Instead, it's something called a semi-direct product. But hopefully it's not hard to convince yourself that each of these row and column flips will double the number of group elements. So at the end, the size of G is just the product of the sizes of all of these component groups, which is 4,608. Once again, the stabilizer of any solution under this action is trivial, so every orbit contains exactly 4,608 solutions. Let's now pick a representative of each orbit. We've already seen that we can use row and column permutations to put the cubes in our preferred positions, and now we can also use row and column swaps to ensure the blue corners of the diagonal cubes are always in the top left. I'm going to call a solution of this form distinguished, and I'll write Y for the set of all distinguished solutions. Each orbit has exactly one distinguished solution, so now all we need to do is find the size of Y and then multiply it by 4,608. This is where things get a little complicated, so I'm going to start using animations instead of demonstrations. The three diagonal cubes all contain the color yellow, so I'm going to collect solutions together based on how these yellows are arranged. More formally, we can define an equivalence relation on Y, which I'll denote with a tilde, where two solutions are equivalent if and only if they have the same yellow cells along the diagonal. I'm then going to write Y mod tilde for the set of equivalence classes under this equivalence relation. Y mod tilde has exactly 27 elements, and we can think of these as 27 Sudoku puzzles which we need to find every solution to. Going through all of these 27 classes would be tedious, so I'm going to introduce one last trick to simplify things. Consider taking a solved grid and swapping blue and yellow. That is, every blue cell becomes yellow and every yellow cell becomes blue. This messes up the positions of the cubes, but because blue and yellow are in the same family, the cubes I end up with are still a valid set of 9 cubes. You can check that taking the transpose will return the cubes to our preferred position, and then we can do row and column flips to get the diagonal blues back in their top left corners to obtain a new distinguished solution. Let's call this transformation F1. Another transformation I can do is to cycle the colors green, orange, and white. Once again, because green, orange, and white are in the same family, we get a valid solution out of this and can use the action of G to turn it into a distinguished solution. Let's call this transformation F2, and let's write H for the group generated by F1 and F2. H acts on Y, but unfortunately the orbits are not all the same size. For example, this solution is unaffected by F1 and F2, so its orbit has only one element. This is the other extreme of the orbit stabilizer theorem, where the stabilizer is the entirety of H. However, H does have a useful property, which is that it descends to a well-defined action on the set of equivalence classes. That is, if two distinguished solutions have matching yellow cells along the diagonal, then applying F1 to both of them gives two solutions which again have matching yellow cells, and the same holds for F2. Moreover, group elements are invertible, so the functions between the equivalence classes are also invertible as well. That means that if two equivalence classes of Y are in the same orbit of H, then they contain the same number of elements. So we just need to enumerate the solutions of one representative of each orbit, and that will give us solutions for all of the others. It's not hard to find all the orbits of H on wide mod tilde. There's one with one family, one with two families, and the remaining ones have 6 families. Picking a representative from each of these orbits, we have now cut down our 27 Sudoku puzzles to just 6. It's still a little tedious to enumerate the solutions to all of these, but it's just about doable by hand and very easy to do on a computer. Each of these 6 families has between 18 and 26 solutions, and if we take those numbers and multiply them by the size of the corresponding orbit, then add them all together, we get 578. Recall that this is the number of elements of Y, and to get the number of elements of our solution space X, we need to multiply by 4,608, which means, finally, the total number of solutions is 2,663,424. Now, the packaging says that there are only 500,000 solutions, so I suspect what's going on here is that the designers consider 2 solutions to be the same if you can rotate the grid to get from one to the other. In other words, the actual solution space is the quotient of X by the action of the rotation group of the square. This cuts down the solution space by a factor of 4, giving 665,856 solutions. From searching around, I discovered an older version of the game manual which states that the number of solutions is exactly this number, which means we did the maths correctly. Hooray! The old manual also states that the total number of ways of fitting the 9 cubes into the grid is about 2.6 trillion. That number is actually much easier to compute. There's 9 factorial ways of positioning the cubes, and then 24 to the 9 ways of rotating them, and that gives a much bigger number? This 2.6 trillion number is actually just 24 to the 9, which means the designer forgot that the cubes can be reordered, apparently. Now, my manual doesn't have this page, so maybe what happened is that someone at ThinkFun realized that this bigger number was incorrect, but rather than correct it, they just removed all references to this number and the exact number of solutions got cut with it. I think this says a lot about our society.